Everyone, just going to give it a minute or two for people to log in here before we start for the day. Rebecca, can you see my screen? It's good. It just looks kind of funny on here for a minute.
Yep, I can see your screen. All good.
All right, you can see my slide.
Yeah.
Gotcha. It looks just super wacky on my screen, but as long as it's coming through all right. So thanks again for coming. I hear there were some audio visual issues last week. Hopefully we had that all ironed out. I'm actually just coming back from paternity leave, so hopefully if you were looking for me and you didn't hear from me, I will be able to get back to you soon. So just before we start, I wanted to say a correction and an apology from last week. So we do what we can as best as we can, or we need to be 100% at crediting the images and the data that we use. So I try to be very, very careful about that, or we try to be very, very careful about that. But sometimes things slip through the cracks. So we had an image last week that was actually not attributed. I think it's been fixed in the slides that were updated or that were uploaded. But it's actually this image here, which was used to show Raman mapping at different under different conditions, is actually intellectual property or courtesy of, or was courtesy of VTech. So we didn't credit that. And so thanks to VTech for originally providing that. And it's been fixed in the updated version. It's particularly egregious because VTech is actually another Oxford Instruments company, as is Andor. That being said, just if you go back and look at the slides again or look at the videos again, I believe that's been fixed, but just wanted to clarify that because we need to make sure that we're clear about what's our work, what's someone else's work, and where things come from, right? We need to give credit, and hopefully we haven't missed anything else. So that being said, let me turn this over again to to Rebecca here. Rebecca, can you take control? My window is got all wacky here. Hi everyone, welcome back to our fourth session of Introduction to Raman Spectroscopy. And today is going to be all about resonance Raman. Again, I'm Adam Wise, an application specialist at Andor. And welcome back. So during your last session, or during our last session, which hopefully you caught, you would have seen my colleague Shane Harrell discussing Raman spectroscopy of 2D materials. If you have any questions about that didn't get answered, let us know. I am back in the office now after being away for a bit. Today, we're going to take a closer look, like I mentioned, at resonance Raman spectroscopy, which is surprisingly different than what we've been talking about before. The methods and the materials will be very much the same, but the effects and the interpretation will be a bit different. And we'll take a tour through a resonance Raman application, which is to say conjugated polymer photovoltaics and doing some things in those systems. And if you're just joining us again, or if you need a refresher, just a reminder that Raman spectroscopy looks at light that is inelastically scattered off materials. It's inelastic because we lose, or sometimes but more rarely gain, some energy to molecular and lattice vibrations. The molecular vibrations interact with light, or vibrations of any sort interact with light through polarizability changes that come along with the vibration. And we talked a little bit about a pretty hand-wavy but highly explanatory mechanism for how that interaction works on our first day, I believe. So if you want a refresher on that, just run back to the first one available on the Andor Learning Center. However, real molecules do more than vibrate. And what I mean by that is that real molecules don't just have nuclear vibrations where the nuclei are bouncing back and forth, they also have electronic excited states. And now our question becomes, what happens when we start to push our light that's coming in closer to a resonance with an electronic transition? So just as an aside, I've tried to move my head picture here, my video, such that you can see the figures and you can see the citations and such. The slides will also be coming out that you won't see my video on, so just the links will be clickable and you can see things that are not obscured. So hopefully I've made it so that you can see the actual figures and not just my video feed here. So the question is, up until now, I've been a little bit cagey about what resonance Raman means. I think I showed a few resonance Raman spectra at the beginning, possibly on day 1 or 2. And I said, don't worry about it for now. Resonance Raman spectra are just like Raman spectra qualitatively. And they are. They use the same methods and materials. They look the same. You can see some up here. Those are resonance Raman spectra, and we'll talk about where they come from shortly. And they're recorded in the same way. They show the same things. These peaks are energy loss from a light input that we're putting in there that is related to molecular vibrations. But the question is, what happens when our light that is scattered off starts to approach an electronic transition, or starts to approach an electronic absorption here? So you can see this is a iron coordination compound, or organometallic coordination compound, and we can see it's got a strong absorption here, which is where we're going to promote some electron or electrons in there from ground state to an excited state. And you can see that this is an absorption in the green. It doesn't particularly absorb red light. Here's yellow, green, blue, very, very blue. And that's where that absorption is happening. That's where it will actually take light and it will do something with it. It will cause a real excitation in the molecule. You can see an inset here. Here's what the solution of this actually looks like as you increase the molarity. And unsurprisingly, it's a red solution, because the red light is allowed to pass unhindered through there without getting absorbed and either scattered somewhere else or thermalized and turned into vibrations or heat in there. So the question becomes, we've been working out here, we've been working off resonance, non-resonant Raman spectra that are purely about interactions with with molecular vibrations without bringing electrons or without bringing excited electronic states into there. So what happens as we push further and closer into that electronic transitions resonance, or into that absorption band here? It doesn't seem like it would really matter at first, other than potentially allowing for photoluminescence. But I'd like you just to look empirically, or think about this empirically. So out here we have 647. These are lines of an argon ion laser here. And you can see 647 is out here. We're way off resonance. And we have a spectrum that looks like this. Then as we push further and further into that resonance, you can see now all of a sudden we have other vibrations that are coming in. Either they were very weak before or they were almost invisible, and they're coming into the spectrum. So as we go closer and closer to on resonance, all of a sudden you can see the distribution and the intensity and the relative intensities are quite different, possibly also some small frequency changes as well. Here, this spectrum actually shows an internal standard. So in the solution is our sulfate ions that Raman scatter as well. They scatter non-resonantly, so we don't have to worry about them being changed as we change the frequency of our scattering light, of our light to be scattered. So this is an internal standard. It's a internal, something that's in with the sample or in with our unknown, that provides a steady peak that we can sort of calibrate off of. And that internal standard is really helpful, because you can see here the internal standard dominates. Our spectrum of our coordination compound is very weak. And then as we go closer and closer to resonance, and we're on resonance, you can see all of a sudden, relatively, and this is scaled, normalized, relatively our Raman spectrum from our compound has become very, very, very bright. We've had quite a bit of enhancement. So not only have we had different bands come into play, and I think you'll see it a little more closely next time, but different bands getting enhanced more than others, we have a general enhancement. So let's talk about this more in a second. So the practical effects of resonance Raman are several. As you move onto an electronic resonance or electronic absorption of a molecule with our scattering light in terms of wavelength or frequency, however you want to think about it, two things happen, or two very obvious things happen. More subtle things happen as well. The first is that resonance Raman enhances scattering. It makes the scattering more likely, increases the cross-section. It could be just a small factor. It could be orders of magnitude, depending on the particular system we're looking at. So if you remember, I said that the sulfate ions here are an internal standard. You can see that scattering. So here's this is kind of our standard candle here, sulfate, and has one band out here. And you can see that as we go onto resonance, our scattering is enhanced by a factor of somewhere around 100. It's hard to exactly quantify, and I just wanted to give a hand-wavy number there. But a factor of 100 is nothing to sneeze at. So we're getting quite a bit more in terms of practically just getting more signal out. And who doesn't like more signal? However, the thing is, not all vibrational modes are enhanced or enhanced equally. So you can see here, I tried to draw a little guide for the eye, but at our off resonance versus our pre-resonant versus our resonant here, you can see the slope of the first mode to the fourth mode or fifth mode here changes quite a bit. It gets narrower, lower and lower slope as we go up there. What that means exactly, we'll talk about shortly, but you might say, oh, we had a hard enough time identifying things simply based on this complex forest of peaks. Now you're telling me that depending on how I excite them, with what wavelength, those spectra might look different. The answer is yes, but there's some method to this that we'll hopefully cover very shortly. So one of the interesting things as well is that if you have a complex mixture, if you have multiple components, and you have some separation between their absorption spectra, then you can target specific parts of a mixture, or even more interestingly, different chromophores on the same molecule. And what I mean by targeting is that you will be on resonance with one component or another component. You'll get the enhancement in that component that you're on resonance with, and you won't on the other components. So you're looking at a mixture of A, B, and C, and we were talking about before, that's one of the complexities of Raman spectroscopy, where what you'll get is you'll get these potentially overlapping spectra weighted by how much of A and B and C are in there. But the thing is, now we can just light up A, we can light up B, we can light up C, assuming that we have the ability to generate light that interacts on resonance with those components, and those components or those species present have different absorption spectra. Not finally, but just as another note, we have overtones and combination bands often present in resonance Raman spectra. And what that means is that you don't just have the fundamentals of this is a, say, this is a 1200 wave number, sorry, 1500 wave number mode. That means it's a Raman shift of 1500 wave numbers. That means it comes from a vibrational mode that has a resonant frequency of 1500 wave numbers in those units. Instead, now we can have a fundamental at 500 wave numbers, then a second harmonic at 1000 wave numbers and 1500 wave numbers, or two modes interacting where you have 1000 and a 500 wave number mode, and that you see a peak in your spectra at 1500 wave numbers. Nothing to worry about right now, but I just wanted to let you know that these spectra can be a bit more complex and interesting, and we'll explain that shortly. Just as an aside, what is it called exactly? And I apologize in advance if I use resonance and resonant inconsistently or interchangeably. So I think it's really called resonance Raman spectroscopy, but it's far from unanimous. I believe resonance is the preferred term, but we will be on resonance, resonantly, doing resonance Raman. So these diagrams I see pop up often, and I don't find them that helpful, but I wanted to include them for completeness' sake. So here is I don't know if we can call this a Jablonski or Jablonski diagram, where we have these states and these ladders going up and down. These are very simple. But what this is a representation of y-axis is energy here. So here at the bottom is our electronic ground state. And here's another sub-level that's a vibrationally excited state in one vibration. So if we had multiple degrees of freedom, we'd have multiples of these that would be kind of orthogonal to each other. And what happens in non-resonant Raman is that we have some far away or possibly non-existent electronic excited state that we don't worry about. All we care about is the electronic ground state. We scatter, where we have a photon come in with some energy, goes up to a virtual state, and gets immediately comes back down to a vibrationally excited ground state. So this would be our Stokes shift, because you can see this arrow in energy, that's the photon in, is a bit longer, a bit higher in terms of energy than the photon that comes out. So this is our Stokes. Then we have our anti-Stokes here, which is represented by a pre-existing vibrationally excited state in the molecule that scatters up or that gets scattered off a virtual state back down to the electronic ground state and vibrational ground state. And that is the gain of one unit, one vibrational quanta here. And I made a note that this spacing is the magnitude of the Raman shift. So here it's Stokes where we lose some energy because this is just going to be left behind. And here the anti-Stokes where we gain some energy, less likely. And I believe that this is so much less likely because we have to have a pre-existing or a present vibrationally excited state, which is highly unlikely with the large energy shifts that we usually deal with. Now, on the other hand, for resonance Raman spectroscopy, all we've included is this electronic excited state that we are now near. The bookkeeping is the same, but we just happen to be close to a electronic excited state that we were somewhat close to resonance with or pre-resonant with, which means that we are sneaking up on its absorption spectra. It doesn't give me a lot of insight into the nature of the phenomenon, but it's, I suppose, a helpful bookkeeping tip, these diagrams. An additional note about overtones and combination bands, and that just means that now we have a slightly more complicated picture here with the electronic ground state decorated or dressed with more vibrational levels. So instead of just scattering off this virtual state and coming back down to the first vibrationally excited ground state, it could be the second or the third one, or I guess 0th, first, second, depending on how you start that numbering. Again, I don't get a tremendous amount of insight from these, but it's neat to see. The actual data, and this is my messy data that looks like this, these are charge transfer complexes. The effect is that all of a sudden now you have, instead of just this fingerprint region here, 1,000 to 2,000 or so, we actually have lots more. And this is not the normal stuff that would be at 3,000 wave numbers, which would be CH stretches. These are overtones and combination bands of these fundamentals over here. So you get this one at 1,600 wave numbers, then you get one at 3,200 wave numbers, and then again at whatever 12 times 4 is, 4,800 wave numbers. So what is the value of this? There's value in terms of calculating things about the nature of the excited state that we're looking at here in terms of its geometry changes. We'll talk about that briefly. I wouldn't worry about significance for the moment, but just don't be surprised if you see them because it can be alarming or it can be shocking. And as you get closer to resonance, these will be more likely to show up with a high magnitude, and it can be pretty wild to see for the first time. You might not know what you're looking at. Or alternatively, you could mistake one of these bands or a combination band and misassign it. So just something to think about. This is one clear visible distinction between resonance Raman and most non-resonant Raman spectra. Most, if not all. I can't think of an exception at the moment, but I just want to hedge. So I just wanted to revisit because I love to go back to the material that we talked about, when possible, and sort of go a little bit deeper into it. So remember these spectra that I showed you for benzene, and this is the benzene Raman and the benzene IR spectra, and I wanted to show sort of how they're complementary. If we have a center of inversion symmetry, then Raman bands and vibrations should either have to be Raman active or IR active, but not both. And you can see that when you have a strong IR absorption, you correspondingly don't have a strong Raman scattering peak. And the question was the question that I have for you now, was this a non-resonant or a resonant Raman spectra? And the two most prominent features in it were you can see my slightly, or not my, ChemTube's slightly exaggerated vibrations here. The one at 3,000 wave numbers where the protons or the hydrogens are stretching symmetrically in a circle. And then the one at 1,000-ish 1,000-ish wave numbers where the carbons are stretching in a circle. Forget if you call that a breathing or just a symmetric stretch. So I want you to sort of think about these two features, these two very strong Raman peaks, and I want you to think about whether this could have been a resonant or non-resonant spectrum, and we'll answer that in a second here. Did I spoil it? I think I might have. But because benzene doesn't absorb very much in the visible at all, I believe, and you can see I had some trouble finding a picture of benzene because benzene is boringly a crystal clear liquid that looks exactly like water, other than having some Slightly different refractive index, a higher refractive index, so it looks to me a little bit more. If you had a cup of benzene and you had a cup of water, other than obviously the smell, you could probably differentiate them based on just how they refract light. So benzene has a negligible absorption in the visible, and we can see, as I mentioned, it's quite clear. It is hard to hit resonance with an electronic transition, and here is the UV absorption of benzene that doesn't really turn on until about 215 nanometers or so. So it is hard with normal light sources to hit resonance with an electronic transition using a commonplace light source. So a normal laser that you might buy cheaply, or a mercury lamp, a deuterium lamp might do it, but I think the continuum light around the Lyman alpha line, which is probably not super strong, which you'd want to be using for Raman anyway, would make it difficult. But if you have the fifth harmonic of a neodymium YAG laser at 212 nanometers, you are good to go, because you can see here, this is certainly not my work. This is from the 80s, before I was born. But you can see your pre-resonant at 212 nanometers here. So the question is, not the question, but that was almost certainly not a resonant Raman spectrum, even though I spoiled it, resonance Raman spectrum, even though I spoiled it, I think, there. But just from an equipment aspect or an equipment concern, you could say probably doesn't have a deep UV light source available. It's so much easier to use a laser in the visible or in the near infrared. So let's talk about benzene resonance Raman real quick. So here is another view of the UV, but still non-resonance Raman spectrum. We have our two peaks here, our nu1 and nu2, little v's, I guess they're Greek news for frequency, but the same vibrational modes. These dotted ones are solvent peaks, so please just squint your eyes and ignore them for the moment. However, as we sneak into the electronic absorption, all of a sudden we get, although you can't quite see it here, we have a higher cross-section, or we have a higher amount of scattering, we have our scattering enhanced. But all of a sudden, our peak at, where is it? Our peak at 3,000 wave numbers utterly disappears. Sorry, a bit above 3,000. It's confusing here. Again, like I mentioned before, we have some combination bands and overtones sneaking in. But if you look for that particular frequency, it's just about one tick over 3,000. It's gone. Why might that be the case? We'll talk about that in a second. You might look at the signal to noise here and say, well, this is nice and clean. This is nice and this is not nice. This is unnice and noisy. These spectra were taken at 1% volume to volume. These are taken at 40% concentration of benzene and I think acetonitrile. So I believe to avoid self-absorption, and I'll talk about that possibly in a minute. But ignore that the y-axis or the noise for now. But let's focus on why that Raman peak disappeared. So the thing is, and I'm so sorry if this is misleading in terms of the picture here, but here's the key idea. Electrons are distributed differently in the electronic ground and excited states. Of course, right? I mean, think about an s to a p orbital or something like that, or HOMO to LUMO transition. Electron distribution is different. It kind of has to be, right? Electrons are going into a different state. However, if those electrons are involved in holding together a molecule, the redistribution of charge changes equilibrium bond shapes. So it could just be bond lengths. It could be some way where the molecule is distorted. But what that does is kind of tweak vibrational modes. They're displaced during electronic transitions. And those vibrations that are along the axis or along the axes of how that molecule is tweaked in the excitation to the, or in changing to an electronic excited state, those are the ones that get enhanced, and that's called Suboy's rule, I believe, or at least that's what Wikipedia called it. I've never actually heard someone say that out loud, but the original work that proposed the rule was by a Japanese group, with the author being a Dr. Tsuboi. So the key thing is here that vibrations that are not involved in the transition are left out in the resonance Raman spectrum. So which ones are going to be displaced, which vibrations are going to be displaced, or which normal modes are going to be displaced, which aren't? And if we think about that, well, this transition from the molecular orbital from one to another doesn't involve the protons, or doesn't change the equilibrium distance of those protons. Those protons are bystanders in this electronic transition. The electronic transition exists on the backbone of this conjugated molecule. So is there an intuitive explanation? The intuitive explanation meaning, is there a way to talk about resonance Raman and how proximity to an electronic transition enhances Raman scattering? So we discussed on the first day a simple model for non-resonant Raman scattering, where we had a toy molecule that has changing polarizability as it vibrates. So it's vibrating, and at some point it's less polarizable, at one point it's more polarizable. And when you have that vibration interacting with a time-varying electric field, then we get these terms that look just like Rayleigh, Stokes, and anti-Stokes scattering. Is that a molecule, sorry, is that a model that describes reality perfectly? No, but I find it very helpful for thinking about. Unfortunately, I don't know a simple model off the top of my head or with some thought or research that explains resonance Raman in the same way. Resonance Raman is surprising, in my opinion. There are frameworks that explain a lot, and here I link to the time-dependent theory of Raman scattering paper by Heller that I think is worth taking a look at if you're curious. I simply ask you to accept the existence of resonance Raman spectroscopy for now, not on faith, but just empirically. It's something very surprising and shocking that happens. And I'm more surprised that it didn't cause some shock during the discovery of Raman spectroscopy, other than they started with clear compounds that didn't have resonances in the visible or in an easily accessible UV part. I'd love to know more about the history of that, and I plan to research that and maybe talk about that a bit more in subsequent lectures. So again, going back to sort of the empirical use and the empirical function of resonance Raman, and I mentioned before that if you have absorption spectra of species in a mixture that differ, you can actually aim your excitation color, your excitation wavelength, or energy, however you want to frame it, and you can selectively probe one component. So this is just an example. It's not unique to this system here, but if you have, these are two different chemicals or two different species in a donor acceptor organic photovoltaic blend, you can see that this is the donor and here's the acceptor. The P3HT has an absorption in the visible over most of the visible. PCBM, which is the C60 derivative, does not. So if we excite out here, we can just selectively probe the P3HT. We could potentially also do the PCBM out here. It's a little bit trickier in terms of the wavelength, but could certainly be done. And the advantage of that, or the utility of that, is that not only will we get an enhancement when we're on resonance with one or the other, but we'll primarily be getting information from that one that we're probing. So even though we have a mixture, if we did a non-resonant Raman spectra, say out here in the near IR, and I apologize if I've been pointing without turning my pointer on, out here in the near IR, say, where we were off resonance with both, we would kind of get a weighted mixture of everything here, these side chains, the backbone, which is fine and might be useful, but if we want to learn information about the part of the molecules that are interacting with the light that we're sending in, which is pretty important if you're talking about photovoltaics or LEDs or something that is, we're looking for information about that light matter interaction, that's quite useful. And just to take it back again to a previous talk, I think this was either the first or the second, I think the second session, explosive detection. I mentioned that Raman spectroscopy was very popular for explosive detection. And it's not just because there's a fairly unique set of spectral features to look for, but, and if you look at here is the UV absorption of a number of common explosives. There's a lot of UV absorption that we could potentially scatter off of and get not just specificity, but also resonance enhancement. So we're getting a fairly unique output, we have a slightly unique input, and we're also getting some resonance enhancement along the way. So it's not just that we can do, look for this unusual band, I think it was the 2000 something wave numbers, a nitrogen bond, but we're also doing it by exciting into the UV, into these UV absorptions, or near these UV absorptions, and we're getting some enhancement as well, which we need if we're going to use this tiny view for doing a standoff Raman with the telescope. So Before I go any further, I think that's been about half an hour. I just wanted to circle back about resonance Raman spectroscopy. So what is it? Well, it's Raman spectroscopy, but it's when the wavelength that you're using is sneaking up or on an electronic absorption of a molecule or of a material. So it's Raman scattering. It's increased when scattered light frequency is near an electronic absorption. So again, only some vibrational modes will be enhanced. Those that are kind of near the excitation. I'm trying to think of a better way to put it. I'm wondering if I should put more examples in there. But those that are affected by the geometry changes going from the ground state equilibrium geometry to the excited state equilibrium geometry of the molecule. So those modes that are displaced, and you can imagine, they're pushed out of the way kind of, are the ones that are enhanced. And we can also selectively pick out molecules or chromophores within a molecule by choosing to be on, or by aiming to be on resonance with them based on the color or the frequency of the energy of the light that we put in, depending on how you want to think about it. Those are all synonymous. So let's pivot quickly into looking at actual experimental systems. It doesn't have to be organic electronics. That's the one that I picked because it's familiar to me and it's a good fit for a couple of reasons. So again, you can do resonance Raman anywhere that you could do Raman and you have some interaction, some electronic absorption that you can excite into or excite near or scatter near. I keep changing my terminology here. It is particularly suited for materials that interact strongly with light because we need, again, some kind of light matter interaction, some visible absorption or UV could be, but just some actual absorption we can work with or near. Ideally, they don't fluoresce because, again, that enhancement might not be enough to get over the amount of fluorescence. It in some systems could put you above, far above where non-resonance Raman would be, and that might be enough to overcome whatever amount of fluorescence is present, but ideally not very brightly fluorescing. Or will work, on the blue side where the fluorescence, the blue side of the absorption, or further into the absorption where we're not going to catch a lot of fluorescence. And we prefer to look at things that have a lot of vibrational info available, so a lot of vibrational modes active, and potentially also have multiple components with different optical properties because we can really exploit our ability to be on resonance with A or with B or with C one at a time if possible. And so just as a really quick introduction, which is not going to be nearly enough, if you're not familiar at all with organic electronic materials, so typically in electronics, organic materials are not part of the main picture. They're used for insulation, say. So we have a wire that has a polymer around it because the polymer doesn't conduct electricity, and you can touch this part without getting shocked, right? You can pull a power cord out of the wall without getting your hand electrocuted, which is very helpful. Alternatively, you could have silicon chips where you have a silicon semiconductor, metal conducting traces, and the only part that organics play is as a potent or as an encapsulant, again, as an insulator or inert material. But the thing is, there are actually conductors and semiconductors that can be made entirely of organic material. So both small molecules and polymers, and they can be electrical semiconductors and conductors depending on how they're doped or how they're prepared. So I just wanted to show you some pictures because I find it quite striking if you haven't seen these things before. So here's some different forms of polyacetylene, which I believe was one of the first really well-studied conducting and semiconducting polymers, depending on how it's prepared. And then this is one of the more popular ones in the world of research as a model system for organic photovoltaics, and that's poly-3-hexylthiophene, P3HT. And you can see these are lustrous, metallic-looking films where they look like a metal foil, and that is because they're either pretty good conductors or semiconductors and reflect quite well. So as far as what they can do, almost anything that an inorganic semiconductor can do, an organic semiconductor can do, or an organic electronic material can do. So that means OLED displays, and these are a real commercial thing that you can buy if you have a little bit more money to spend and you want the best performing, nicest color saturation and best on-off ratio. Just beautiful TVs. I don't have one because they're expensive and I don't really care, but they're really, really beautiful if you see them in person. These are less commercially available, but they're still something that shows a lot of promise simply because they could be made in a way that's very low energy, very low energy required for processing and creation. So photovoltaics and transistors Photovoltaics are, to my mind, the more interesting part than transistors because we have such wonderful transistor technology now. There's not, in terms of how much we need, in terms of square footage, not a lot for transistors, right? Transistors are super small. It's fine if they're super small. On the other hand, photovoltaics, we could really use a lot more energy right now, as clean as possible, as portable as possible, as light as possible. And there is a consistent level of interest in thin film photovoltaics. Organic conjugated polymers are a small part of that, but the draw is that you could do solution processing and you can use basically inkjet printing, things like this to do the processing rather than these very expensive manipulations of silicon and related things, even like other thin film inorganics that require these very intense, energy intense processes. Just real quick, and again, this isn't essential to look at this eye chart right now, but if you haven't seen it, this is NREL, the National Renewable Energy Laboratory in Golden, Colorado, I think, keeps this scorecard that shows these different technologies all competing with each other. And I'm focusing on organic photovoltaics here versus organic transistors, organic LEDs, simply because I think it's civilizationally a more interesting question, a more important question. You can see if you squint your eyes, this link will be clickable when you download the slides, although you can search NREL efficiency chart. This has been just an important tool for many, many years. Let's see, so you can see up here are these multi-junction cells that are usually silicon or something like that, or silicon with another material on it, that have these insane efficiencies that are beyond the thermodynamic limit for a single junction. Up at 48, 50%, that might have some kind of concentrator or some other cheats in there to help juice the power, juice the efficiency. I should double check and make sure I'm not, these are broken out for different concentrator, non-concentrator, so on. OPVs, organic photovoltaics, are usually down here because they're not as efficient. They're generally very cheap and easy to produce. So we were making photovoltaic cells using OPV technology in a small lab scale without it being a huge deal, which would be much more difficult to start with the inputs for a silicon solar cell or something else that was up here. So even though they're lower efficiency so far and overall, although no one knows exactly why, the interest is always there because the idea of doing thin film cheap solar is just very attractive. And I'll show you what that means here. This is an older experimental system that still gets a lot of use, but it's just been studied very closely. So this model system is kind of like the zebrafish of organic photovoltaics. So what these are conjugated polymers blended with some kind of electron acceptor. So it's a donor acceptor system that's kind of analogous to an NP junction in inorganic semiconductors. So it's a conjugated polymer dye that efficiently absorbs light, allowing for very thin films, with some kind of electron donor and electron acceptor that are soluble in organic solvents, can be cast, printed, or spun onto substrates. So you can just really paint these onto surfaces. And again, the draw is that we can make these huge, eventually these huge reel-to-reel solar cells. However, this mixture gives you a complex interface. The structure and device performance can be very variable, batch to batch, even within the same sample, and pretty hard to characterize. Again, my head is covering one of these micrographs here, but this is just showing the fine scale phase segregation that happens when you have these two components mixed. Just as an example of, there's this hidden structure that we can't necessarily probe that well, that's not well characterizable, and is really important to the performance of these materials or performance of these devices, because oftentimes it's the defects that define or limit the performance. So just the more tools that we can bring to bear on these devices, these problems, the better that will be in terms of troubleshooting or figuring out intelligently a way to build better and more efficient devices that can be competitive with silicon. One question worth addressing. We start with a pristine thin film of conjugated polymer, which might be fairly well ordered or at least have well ordered domains, and we add in a bulky electron acceptor molecule at a fairly high loading. We're not doing that after the fact, we're doing this together, but I'm sort of saying, imagine you have this nice pristine sheet where things are allowed to either crystallize or at least to order fairly well, and now we're stuffing in molecules, large bulky molecules, sterically very bulky molecules. So how does that loading, how does the acceptor loading, which is required to maximize performance, we need to put a lot of this acceptor in there, how does it actually affect the way the polymer packs? And there are certainly ways that are not related to Raman spectroscopy to address this question. For example, XRD, where you'd be able to see if it were fairly crystallizable up to the point where you're getting an X-ray diffraction spectrum, or something like GSAX. But this is a way, without bringing X-rays into it, to start to investigate it. So first, why should we care about order or about packing or about these other things that I'm talking about? And I didn't have enough space because I'm already at almost 40 minutes, unfortunately, to provide enough of a case for the importance of this question, which I wish I had in retrospect perhaps. But to move energy, to move charge through these materials efficiently, we need a decent amount of order. Due to the side chains that make these things soluble, that can make it difficult to pack these things well, these things meaning the polymers well in the first place. So we want as much order as possible to make charge transport and energy transport work very well. So resonance Raman, like I mentioned, primarily targets the polymer in this case because we're exciting in the visible on or near resonance just with the polymer, just with the donor, not with the acceptor, not with the C60 derivative. It enhances the scattering by a factor of about 10,000, give or take, which is pretty great in terms of our ability to generate a decent amount of signal from a fairly small illuminated spot when we're doing mapping or things like that. So more importantly, or perhaps in addition, we noticed one particular vibrational mode or one particular Raman peak was increasing and blue shifting was getting enhanced and blue shifting disproportionately in the resonance Raman spectrum as we loaded in more and more dopant. So, we're stuffing more and more of these kind of soccer ball looking molecules with side chains or with solubilizing groups into there. And something is happening. So surprisingly, the Raman spectrum, or the resonance Raman spectrum, doesn't change that much. We don't get that big frequency changes. We don't get huge distributions or changes in distribution of intensity. Just this one peak at around 960 wave numbers. And you can see the high resolution Raman up there showing a small shift, but most visibly an increase in intensity. So the question is, where does that come from? So it turns out this is an out-of-plane vinylene CH WAG, and I've shown in this cartoon here, trying to draw the displacement vectors, but what that is, and I couldn't get this to animate, but if you can imagine my hand is the plane of the molecule. This is a mode that goes in and out of the plane. So this is a symmetric mode, but it's out of the plane of the molecule. It is present in the infrared pretty strongly, as you can see. This is a PPV. These are Raman and IR spectra of the parent polymer without the side chains, polyphenylene vinylene, that's shown here schematically. It's not present in the Raman spectrum, resonant or non-resonant, and it's not, it is quite strong in the infrared spectrum. So it is an infrared allowed vibration. So it is slightly present in the melt and solution phase. So when we disorder that molecule and we twist it up, bang it around, and decrease its planarity, it will be allowed back into the spectrum, into the Raman spectrum. So what we found is that when we pack this film full of, and I'm perhaps leading these questions here, I'm leading this, but when we pack that polymer film full of bulky acceptor molecules, we decrease the planarity. We squish and squeeze and disrupt the packing to the point where we allow a forbidden mode back into the spectrum by twisting up the planarity of the molecule. Of course, it isn't completely gone in the first because those side chains that are attached to the molecule to make it solution soluble or soluble in organic solvents is doing some work for disordering that material in the first place. And it's interesting in of itself, but that we can see a spectroscopic measure of order pretty quickly with resonance Raman is pretty cool. So what I just described is still a bulk measurement, which is to say it averages over a large area or the whole of the sample, and doesn't tell us anything about the point-to-point or the local variation and how that packing works. So one option which we could do to unravel that micron or sub-micron spatial variation is to do confocal hyperspectral microscopy, and that is simply that we're going to illuminate one point of the sample, as small a point as we can using a microscope, and then record a spectrum that corresponds to the scattering and emission from that point. So we're going to use a microscope to focus the excitation light on a small sample, diffraction limited if we're doing really well. And we're going to collect that light that comes from that sample, both scattering and emission, along the same optical path as we use for excitation. And our light from the probe spot will go through the microscope out to a spectrometer and get collected and recorded by a CCD. So for photovoltaics and other optoelectronic things, we can also measure current, voltage, and power conversion efficiency at that spot, which is really important because of the amount of variation both in the chemistry and in the packing and so on, and how that affects the actual device efficiency. So how do you get set up for hyperspectral confocal microscopy measurements? Well, there are really two choices. The first is that you can purchase a more or less turnkey system that integrates a lot of this equipment for you, and there's something to be said for that for sure. We at the time opted to build our own system because we needed an extreme level of flexibility and to integrate some very specific equipment. What we did was we went and integrated a microscope, light source, translation stages, spectrometer detectors, and electrical equipment, all using LabVIEW at the time. It is a very flexible, modular, and extensible choice to do this. And most importantly, it is extremely educational because you will get a chance to get very, very deeply involved with the equipment and the measurements. The other side of that coin is that it is a big commitment of time and expertise, and there's also no guarantee that it will work. Hopefully you will be able to figure it out. So you need to make sure that you're able and willing to give that amount of time and effort to it. There are different levels. So here I show a modular microspectroscopy brochure and notes on adding a spectrometer to a microscope, because there's that where you're building your own system that integrates a lot of equipment, or it could be as simple as putting a spectrometer onto the side of a pre-existing microscope. I would lean more towards that if, for example, I already had a spectrometer or already had a microscope and I was halfway in terms of equipment purchases to having the modules that I needed. Happy if you're on the fence about that, I'm more than happy to discuss that choice offline and to be a sounding board for where you're at. Everyone's situation varies quite a bit, so again, happy to discuss it further with you personally. So what were the spectroscopic points that we were actually looking for with this hyperspectral microscope? Well, specifically in this system, which is another conjugated polymer donor acceptor blend, this is P3HT here. P3HT thermally anneals, or can be thermally annealed, which causes the polymer chains to aggregate. And so that aggregation can be seen in the resonance Raman spectra quite clearly if you have a high resolution Raman spectra that you can record, high resolution resonance Raman spectra that you can record. So if you're looking at that spectrum with sufficiently high spectral resolution, so here is the overall spectrum, which is dominated by a peak in here. That's a carbon-carbon double bond stretch. That is actually two overlapping peaks if you look at it with a high resolution. This window here is only 50 wave numbers wide. So we're looking at a shift of just a few wave numbers here, something like 10 wave numbers or so. And this peak that appears to be one is actually two superimposed. One of them corresponds to aggregated P3HT chains, the other one to unaggregated P3HT chains. So that can also be seen in the absorption spectra here, and I don't want to get too deep into what's going on here because it's a long story. Happy to discuss it further, but the key point was that our group, and by our group I specifically mean the first author here, Yang-Chen Gao, hope he's doing all right out there, realized that you could use this as a metric for aggregation, and it's a very fast and very, I hesitate to say easy, but a clear sign of the state of the polymer that you're looking at. And the really interesting part is that we can use this spectroscopic metric of order or of aggregation to compare with the actual photocurrent generated in a functioning solar cell. So hyperspectral confocal Raman microscopy, hyperspectral confocal resonance Raman microscopy can match microscale structure and composition to performance if you have the equipment suitable for both measuring the spectra on a confocal scale as well as measuring the nanoamps of current that you're generating with your light that you're using to generate the spectra. So it can quantify the presence of polymer, how much or how little of polymer is in a region, because we're looking at the overall scattered intensity. Its aggregation state is that is that polymer ordered or disordered in the sense of, is it collapsed into an aggregated state or not, and how much photocurrent is coming out of that area of the solar cell. So it turns out that if you look at, and this is a tiny patch, this is a 3 micron scale bar, a tiny patch of a functional device, you can see that there's quite a bit of contrast in the carbon-carbon double bond stretch Raman intensity. So this is a PCVM aggregate in here. This is, I believe I showed you a few slides ago, you have these little spots that grow with thermal annealing. Some thermal annealing is required to get the device performance maximally efficient, but too much, and you get this over phase segregation here. But not only can you see a lack of polymer in this PCVM aggregate, I guess it's displaced the polymer around it or grown over the polymer around it as the PCVM is coalesced and aggregated. But we can actually see the metrics of order and disorder in that polymer as far as the aggregated versus unaggregated carbon double bond Raman peak. So we can look and actually see, how is that polymer arranged around different areas, and you can see that the aggregated is higher here and less high here. And furthermore, you can actually see the photocurrent from the device. So the photocurrent is actually worse in areas where segregation has become too high, which kind of makes sense in that you need as much interface as possible to do efficient charge separation and then get that out for use in the device. So I wish I had more time. I'm already closing in on an hour. So I just wanted to show some really interesting, or at least interesting to me, applications of resonance Raman spectroscopy, doing things that you couldn't otherwise do with some research and some preparation. And whoops. I wanted to cut it off here for now and leave some time for questions. But first, I want to say thanks again for your attention through this short course, which has been already a few hours and spanned several weeks. If you have questions, please send them to me, a.wise@andor.com, or my colleague, if it's related to his, Shane.Harrell at oxinst.com. So additional material is going to come through on the Andor Learning Center. So we're going to have a few supplementary external speakers come in to talk about their Raman-related research. And that will be posted to the Andor Learning Center, which is linked up above. And we'll also probably send out emails as they are scheduled. But I also wanted to link, and this will be clickable when you look at the slides, to some other Learning Center material that's relevant to this course. So overcoming difficulties presented by challenging samples, probing molecular structure with low frequency Raman spectroscopy, which is a whole world that I barely even broached, and another one for use in for biosensor applications. So that's all for today. That's closing in on an hour, and I wanted to leave some time in the slot for questions. So thank you again so much for your attention and for coming back for a fourth helping. And there will be, again, a few more sessions by other speakers that are related to this topic that will also post to the course and to the Learning Center. All right, so let's hear from the questions in a minute. I'm just going to give it a second for them to accumulate, and then I'll hop back on the stream. Everyone, just taking a look at the questions that are coming through. I only have a few minutes to answer these today. And first of all, Evangelist, thank you for your congratulations. You might hear the wonderful screams of a baby going on in the background there. So hopefully it wasn't too bad. All right, so just a couple of quick questions here. First, so I'm being asked, what do you actually mean by resonance? And I always get concerned because when I'm saying something, it's like there are so many definitions and so many prerequisites for the terminology. And so literally all I mean by being resonant and is you have the color or the wavelength of the frequency, or sorry, color, wavelength, or frequency of the light that you're using to scatter off the material is on or near part of the absorption spectrum of what you're trying to look at. And the resonance part of that comes in terms of just, if you think about like physical or mechanical resonance, like you're pushing someone on a swing, you can't decide to push at whatever frequency you would like at least without causing trouble. If you push someone like this on a swing at 10 hertz, you're just going to annoy them and push them off the swing. If you want to actually transfer energy into that system, you have to push it at the resonant frequency. You have to push it at the frequency that it wants, quote unquote, wants to oscillate at. So that frequency is whatever the frequency is of the electronic transition. So whatever an electronic transition meaning you have an electronic ground state or some low energy electronic state, you have some low energy arrangement of electrons, and to get it to a higher excited state, you hit it with a particular frequency of electromagnetic radiation or electromagnetic field, whatever. And it has to be at that particular frequency. So that's what I mean by resonant here, is that literally you look at the absorption spectrum and then you say, well, look at the electronic absorption spectrum. And by that, I just mean to contrast it with, the IR absorption spectrum or some other mechanism there. And for example, if you had like a turbid solution in it and you had an absorption spectrum that's really just an absorption and scattering spectrum. So I mean, you have to absorb into an electronic excited state. And for most dilute solutions, dilute samples, I mean, that's what you're going to be looking at in the visible UV, maybe even near IR with some things. So that's what I mean by resonance, just to clarify that. And I hope I hope the rest of the presentation wasn't incomprehensible if I'm leaving that out. All right, just one more question. So on a related note, how do you know whether something is resonant or pre-resonant or off resonance? So I think I maybe was a little bit fast and loose with that terminology, because I would show an absorption spectrum and I'd show, okay, here's one that's sort of far away, quote unquote, from the electronic absorption. Here's one that's kind of on the tail, and then here's one that's in, where it has a very high optical density, where it's absorbing very strongly. So you have a molecule that absorbs strongly in blue, and then maybe the infrared, we for sure know is not interacting. Then maybe as it gets closer and closer, how do you tell when you say resonant, pre-resonant, or off resonance? And to be honest, I've never really thought about a super firm cutoff for that. I've heard a few hundred wave numbers from the onset would be enough to call it pre-resonant. Then once you're past that, that's resonant. There's different consequences of those two cases that you can take a look at the Eric Heller, the time-dependent theory of Raman spectroscopy paper that I linked to. But other than that, I think it's kind of depends on who you ask. Also, a lot of the material that I showed, or a lot of the systems that I showed, have pretty broad absorption, so I think that makes it a little bit harder to tell, because I'm showing pre-resonant as being just below the electronic transition, and that might be more clearly in like a gas or diffuse single molecules versus like a solid or a liquid. So other than that, my brain is still pretty fried from being on leave. If you have questions that I didn't get to, please send me an email. But other than that, thanks again for your attention through the hour, and I see quite a few of you made it through. So thanks again, especially if you made it through all 4 of these so far. Congratulations, or congratulations / thank you for having that attention span. And that's it for me today. Thanks again. I'm Adam Wise, an applications specialist at Andor Technology, which is an Oxford Instruments company. All right, thanks. That's it for today.